So yeah, thanks to everybody for coming. There are no formal, evaluations for people to fill out like there were for the first one, but we would appreciate anybody giving feedback or certainly asking questions at the end of each presentation. That would be great. And I am recording, so if one of the other sessions you're not able to come and you want to see that, I will be posting these in the Capstone library. And I think that's it. We'll do the same question format that we always do, where, wait till the end of the presentation. You can type your question in the chat. If you would like to speak up and ask the question, that's fine too. And then for the presenter, I don't think that the chat gets captured in the Zoom. So if you just read the question before answering it. So I will stop talking and let you go, Rowan. So you can start when you're ready and you can share your screen when you're ready.
One moment, sorry, I can't view the slide button. There we go. Sorry about that. Okay. Welcome to my presentation. My project is called Deep Learning versus Supervised Classification in Remote Sensing, a comparative case study on tree classification. So a bit of background, just to start. And I've used some of the images from the project as background for my intermittent slide. So this is California. So a bit about me. I started working in the field of GIS in 2018 as a technician doing QC at Lux Carter. And Lux Carter is still where I work now, and I became a permanent member there at the beginning of 2021. So I chose to do my capstone on a topic directly related to my work. So Lux Carter is a digital mapping solutions company. They've been in the industry for over 30 years, and they have offices in Cape Town, which is where I am, France, and Tunisia. And they cater to the wireless technology, simulation and training markets, and mapping of smart cities. So some background on deep learning. So I've divided it into machine learning and deep learning. Machine learning is an algorithm-driven engine that can perform complex geoprocessing, such as classification using vector machine algorithms, clustering, which separates meaningful clusters from the rest of the input points, and prediction algorithms like geographically weighted regression. But an expert is still going to need to feed the machine all of these factors so that the machine can then do its job. Deep learning can do all of the above, but the machine figures the factors out itself by looking at the data. So it works more like a human brain, solving problems on the fly. And the more training data that gets put in, the smarter the machine becomes. So the goals and objectives for my project were to do a case study executing 3 different workflows with the same goal on the same data. So the first one is deep learning. The second one is deep learning using a fine-tuned base model. And the third method is a random forest classification using a script that Lux Carter already has. And I chose 3 study areas representing different kinds of vegetation and terrain. So I chose California, Sweden, and Ecuador, because they have very different types of trees. And then I finished by doing an accuracy assessment for all 3 areas and methods to compare them. So here you can see my study areas from left to right: California, Sweden, and Ecuador. And then for a bit of geographic context, here are the areas again. For California, Northern California, because it is quite forested and it's a mountainous region, just for some variety. So my main question is whether deep learning is more efficient than other methods of classification. It is a rapidly growing field and it's getting better all the time. And it has generally made classifying large amounts of data quicker, easier, and less expensive, and can be more hands-off than older methods, depending on how advanced the model is. But it might not always be more hands-off, and it might not always be more efficient. So that's what I was trying to answer in this project. I wanted to know whether there are cases where a classic method might be just as good as deep learning in that situation. So for my methodology, I began with data pre-processing, which included accessing the Sentinel-2 imagery from LuxCarter's server in the form of 4 different tiles for each study area for a total of 400 square kilometers. And I chose each tile individually to make sure that I got the best quality image to make up the entire mosaic. I then prepared the imagery in Global Mapper to make my working images. This is California, showed in natural color, and then Ecuador and Sweden. So for the deep learning based model workflow, it begins with creating a working image, a 4-band Sentinel from 4-band Sentinel-2 data using a band reorder script. And then for prediction, you run the master prediction script on the RGN image using the base model, and then you run another script to extract trees from that prediction. And then after that, you vectorize the tree raster using the raster to polygon tool in ArcGIS Pro. You open the vector layer in QGIS and delete all the polygons classed as 0. And then you QC the remaining tree polygons if needed and re-rasterize. So this is the California base deep learning vector output. So no input from me, this is just the base model. And then here's the Ecuador base model and the Sweden, base vector, and the Sweden base vector here. So for the fine-tuned deep learning workflow, I then create training samples from the working images, name them image 1, image 2, etc. And then clip sample tree vectors from that vector output that I just showed in the previous slides. I then clean up the vectors, add in missing trees as necessary, rasterize that, and name it label 1. So for the workflow, the naming convention is very important because of the in-house workflow and scripts that have been made. I then run fine-tuning scripts in a sequence using image 1 and labels 1 as the input, and then retrain the base model using those training samples. And after that, I do the exact same workflow again as the base learning model, just running the prediction again and extracting the trees. And if necessary, this is where I would do additional training samples. So here is California, and you can see where I've added in the vectors around missing areas. This is pre-rasterizing, obviously. And then here is Ecuador and Sweden. So already you can definitely see the difference in the landscapes, just based on the shape of the vectors that I'm having to add. So then the last workflow is for the random forest classification, which begins with creating training data. So I start with a shapefile in QGIS and draw training polygons representing 2 classes, tree and not tree, using the Sentinel-2 data displayed in false color as the reference. I then run the LuxCarter random forest classification script using the 4-band imagery and the training shapefile as the input. And then after that is when I would do the accuracy assessment. So for the accuracy assessment, I did it using ArcGIS Pro. And I used the same reference data points for each image to assess the accuracy of each workflow. And I was basically comparing it on the confusion matrix, the time spent training the data, and the time spent processing the data. So here are the two main tools that I used in ArcGIS Pro, which is create accuracy assessment points and then update accuracy assessment points when I change the image. So here are the subset of the accuracy reference data points for California and for Ecuador and for Sweden. So comparing landscapes, it was very apparent from the beginning that they would perform differently, or at least this was my hypothesis, based on the difference in the landscape. So California had sparse, scrubby mountainsides, patches of possible wildfire damage with inconsistent trees. Ecuador was great because it was almost entirely covered in dense trees. So the fine tuning was very easy because I could just draw large polygons surrounding any missing areas. Sweden was very challenging to work with because of the amount of lakes and marshy areas with trees blending into water. I ended up having to do 2 training samples for Sweden because of the landscape. So this is just, you can see what I was using for reference data. So it's each of the images displayed in false color. Here's California, Ecuador, and Sweden. So then the results of my accuracy assessments. So the base model for California, I ended up with a producer's accuracy of 70%. And then after the fine-tuned model, my producer's accuracy went down to 67%, which has never happened to me before, but this was one of the challenges of this project and essentially why I wanted to do this project, because I had never looked at the actual difference pre-fine-tuning and post. So it was just interesting to see what might have happened to make it different. Whereas with the random forest method, it was the same 60%, 67% as the fine-tuned version. So on this, the base model actually performed better than either my version or the random forest version. Ecuador, as I already said, was great, produces accuracy of 96% for the base model, 97% for the fine-tuned model, and 99% for the random forest classification. Sweden started the base model very low at 43% producer's accuracy. After my fine tuning, it was slightly gratifying to see that the producer's accuracy went up to 65%. But the random forest classification definitely came out on top with 85%. So it's very interesting to see. To compare the results, I was looking at efficiency based on a number of factors such as time, resources, and the landscape characteristics. So for California, I would say that either method would work, but random forest was quicker to execute. Ecuador, again, they both achieved similar results and random forest was quicker. But for Sweden, random forest definitely came out on top. So if I were to work with a landscape like that in future, I would immediately suggest going with random forest classification. So for the base model, this is just the time that it took to predict and to vectorize. For fine tuning, 3.5 hours, 6.5 hours total for Sweden, 2 hours, 2 hours and 15 minutes. So there's a lot more hands-on time. And random forest was pretty quick in comparison. So as I have alluded to, there were definitely challenges based on the landscapes, some being much harder to digitize than others, Sweden particularly. But the limits of the data are also something I ran into a lot because 10-meter resolution can make it quite difficult to discern what I'm looking at. And then just the limits of the human eye and visual interpretation. And it's always going to be somewhat subjective, especially because it was just me doing it individually and I didn't have anyone to bounce off or to back me up or say, no, I disagree, that's not a tree. But for Lux Carta, I think while this case study was interesting, it's a moot point because of the amount of time and data that's already been fed into the base model. So it's always getting better. And I think we should just keep using it because it works. But if it was up to me, I would use random forest classification for landscapes like these. Thank you for listening. Please feel free to ask questions. Any and all feedback is welcome and appreciated. And I look forward to hearing everyone else's.
Thanks, Rowan. Does anybody have any questions?
If I can get chat up.
None there yet, but I'm assuming some people are typing. Great job, by the way.
Thank you. Okay, so Jennifer says, why the use of QGIS and Pro? So at my company, various teams seem to have their own preferred software. So when I first started working there, I used Map Info for almost everything. And then I got a new supervisor and she prefers QGIS over anything else. So I use QGIS because that's what I use daily when executing this workflow for similar projects. And ArcGIS Pro is mainly because it's a lot quicker, but daily at work, we only have, I think there are 15 people in the office and we only have 3 concurrent licenses for Pro. So I like to use it quickly for short things, but otherwise QGIS. Fritz says, while you worked with trees and not trees, how do you think your approach would work with other land cover types like urban and not urban, or agriculture and not agriculture? So firstly, when I execute this workflow, usually I'm doing 4 land cover classes. So we have other scripts to extract grass and barren, and then there's shrub or sparse vegetation, and then there's tree. And then they get stacked in the end for the final product. I chose to just do tree and not tree because it is sort of easily separate from the other 2 classes. But the other teams at work do urban extraction mainly, and I would think that it would be harder. Well, no, maybe not. Agriculture, I think, would be easier because just by nature of fields, they're, I think, more easily discernible as fields. But urban, I'm not sure. I think that would be more complex just based on the number of different classes within urban that then get separated for the final product. How did your work team / colleagues respond to these results? I haven't shared my final results yet, but I definitely will after this presentation. I'm anticipating, because within my team, which is the production team, and I work closely with the R&D team as well, this deep learning base model is like their baby. They're very excited about it. They've been working on it very hard for the last 2 years. And the last time I suggested using random forest, it was not received very well. But I think if I show them the time efficiency that I found, then maybe I can persuade them. that in some situations it might be more useful.
Okay, great job, Rowan. That's fascinating about how you have to sort of massage your answers back to your colleagues, but
Cool,
but
thank you.
yeah, great job and almost graduated. Yay.
Yay.
Okay, so Bridget is next. So Bridget Wall, whenever you want to start sharing your screen, you can go ahead and do that and see if we can hear you in audio.
Can you hear me?
Yes, we can.
All right, awesome. Okay, good morning or afternoon, wherever you all may be. My name is Bridget Wall, and I'm going to present my capstone on NDVI changes near refugee, internally displaced person, or IDP, and asylum sites in Niger's Tillaberi region from 2014 to 2021. My advisor, Dr. Erica Smithwick, gave me a tremendous amount of guidance throughout the capstone process, and that didn't go unnoticed. So thank you, Erica. All right, without further ado, here's what we'll discuss today. I'll start with an intro to the project, then discuss some key background information on the major issues I address, and go through the methodology, followed by presentation of results and a brief discussion and conclusion of my findings. All right, Niger is a landlocked country in West Africa. It's bordered by, as you can see on the map, Algeria and Libya to the north, Burkina Faso and Mali to the west, Nigeria to the south, and Chad to the east. For this project, we're going to focus on the Tillaberi region in the black box to the bottom left of the country. Niger encompasses the Sahara Desert to the north, the Sahel, which was a once grassy and now semi-arid strip of land across the central belt. And there's also a tropical climate to the south. And the majority of the country's about 24 million people live in the south, which is much more favorable to agricultural and pastoral activities compared to the northern desert. The country shares a multitude of sustained and developing crises, including food shortages, decreasing vegetation cover as a result of land degradation, natural disasters, including flooding and droughts, violence, political instability, disease, and growing refugee and IDP populations, just to name a few issues. The country has received last place on the Human Development Index since the 1980s. And the Tillaberi region specifically is a focal point for the majority of the issues that I just stated, mostly due to growing populations, a rapidly changing landscape, and the presence of violent extremism. The purpose of my project is to highlight the increasing refugee and IDP crises and its impact on the surrounding environment of the Tillaberi region. And over time, there's been macro scale environmental changes gradually taking hold throughout the African continent and the Sahel, specifically due to climate change. But a recent study suggests that micro level yet noticeable decreases in vegetation cover due to land degradation may be occurring in areas surrounding refugee camps. There is a United Nations Convention to Combat Desertification, we'll call it UNCCD, and they define land degradation as a reduction or loss of the biological or economic productivity that resulting from land uses or from a process or combination of processes, including processes arising from human activities and habitation patterns. These findings can likely be explained by the environmental demand as a result of increasing camp populations and a lack of measures to properly maintain a sustainable landscape in the area. And then these simultaneous macro and micro level changes could then increase the rate at which the Tillaberi region's environment is degrading, which in turn could exacerbate the country's current issues. So the project's question is as follows. Between 2014 and 2021 in Niger's Tillaberi region, are changes in vegetation cover in areas that fall directly outside of refugee, IDP, and asylum sites consistent with the region's trends towards land degradation as a result of desertification? And then if I do find inconsistencies between regional trends and changes in vegetation cover to areas that fall directly outside of these sites, this will likely indicate that the micro level anthropogenic environmental changes surrounding these locations are significant enough to stand out from these gradual trends towards desertification. And then any findings then drive the need for further research on the environmental impact due to increased number of refugees, IDPs, and asylum seekers. So a little bit of background. This map shows the Tilbury region in the blue container. You can see based on the hashes that the region lies pretty much entirely within the Sahel. Over the past several decades, the Sahara has crept further down south in a process known as desertification, which can be defined as land degradation in arid, semi-arid, or dry subhuman areas as a result of various factors to include both climatic variations and human activities. One study revealed that vegetation growth along the Sahara-Sahel margin crept almost 130 kilometers south between 1980 and 1990, and this process is only continuing over time. And then, so here's a quick background on the factors driving the increase in refugees, IDPs, and asylum seekers. So since 2012, violent extremist groups inspired by both Islamic State and Al-Qaeda in Mali and Burkina Faso have increased in both presence and number of attacks. So as a result, most of the affected refugees fled to the neighboring Tilbury region in Niger in an attempt to escape the violence. And then in 2019, the conflict shifted when these violent extremist groups, or VEOs, specifically JNIM and the Islamic State in the Greater Sahara, or we'll call it ISIS-GS, expanded operations into Niger's Tilbury region. In the northern Tilbury region near the Malian border, Nigerian government forces were forced to flee from their held positions as many units were overrun and cut off from resupply. And then, so though these military forces, supplemented by both France and other Sahel countries, eventually regained some of the lost territory, the number of attacks and casualties continued to increase into 2020, likely just due to the increasing number within the two violent extremist groups in the region. Attacks then continued into 2021, including a January raid on 2 villages in Tilbury, which killed over 100 civilians, which marked one of the country's deadliest events in recent history. So the map below are depictions of JNIM and ISIS-GS attacks in the Tilbury region between March 2018 and March 2021. Just something to note, due to the lack of available data, the map for 2021 only depicts the number of attacks from the year's first 2.5 months, but it does show rather a high volume of attacks given a shorter time frame. As of 31 January 2021, the number of IDPs in Niger reached just over 130,000, which is a 50% increase from the year prior. The number of Malian refugees on 31 January was just over 60,000, while there were less than 4,000 Burkinabe refugees. The influx of refugees, IDPs, and asylum seekers in recent years has added stress in the region. One study found evidence of refugee-contributed causes to a changing landscape throughout the African continent, mostly due to agricultural expansion and deforestation. Then another study found a almost 12% natural resource decrease within 5 kilometers of refugee camps in Kenya between 1997 and 2014. An increased demand for food and resources due to growing populations, combined with unfamiliarity with the local ecology, resulting in unsustainable agricultural practices and overgrazing, are likely the driving factors behind landscape changes surrounding these sites. So I obtained Landsat 8 imagery, 30 meter resolution used in the analysis for both 2014 and 2021 years from the USGS Earth Explorer site. Each scene consisted of 11 bands in UTM zone 31 in meters with the WGS 1984 datum. I also used refugee and IDP location data from the United Nations People of Concern location shapefile. And I also obtained a shapefile of Niger's 7 regions that I would eventually utilize to clip imagery to reside solely within the Tilbury region. And then I solely used ArcGIS Pro throughout the entirety of the project. So for the analysis, prior to conducting the imagery required pre-processing, so for each downloaded scene for both 2014 and 2021, I used composite bands tool to combine each of the scene's 11 bands into one single multi-band image, and then utilize the mosaic tool to create mosaic of imagery for both years. And then now that I had 2 fully mosaicked imagery layers for both years, I used extract by mask to extract the applicable mosaic imagery that fell within the Tillaberi region boundary. And then I changed band combinations to reflect a true color composite image. And then following pre-processing, I conducted the analysis for both 2014 and 2021 clipped mosaics. I then utilized the NDVI rasters function tool using the bands 4 and 5, red and near infrared, to create an NDVI layer for each raster. And then I used the 2014 and 2021 NDVI layers to input them into the compute change tool, which created a raster layer depicting NDVI differences between the 2 years throughout the region. I then utilized the step-by-step classification wizard to create 3 individual class categories from 2014 to 2021, NDVI difference layer based on the different values of each pixel, excuse me. And then the 3 categories were then classified as negative change, no change, or positive change, as you can see on the image. And then following the general NDVI change analysis across the Tillaberi region, I then analyzed the number of pixels within both 1 and 8 mile buffers for each refugee, IDP, and asylum site that experienced negative, positive, or no NDVI change between 2014 and 2021. To do this, I utilized the buffer tool in ArcGIS, selecting the site location layer as the input and defining the distance as 1 and 8 miles on 2 separate iterations of the tool, and then utilized the summarized categorical raster tool, selected each buffer as the area of interest, and then that resulted in a series of tables depicting the number of pixels in each NDVI change category solely within each buffer. And then I combined the tables into Excel tables at 1 mile and 8 mile scales, and then you'll see it in my results section. So challenges, when I conducted the analysis, I faced numerous challenges and setbacks. So first, although I intended on zeroing out areas covered by clouds, I was ultimately unsuccessful for the year 2021. So I opted to accept a certain degree of error in my analysis by keeping the clipped mosaics with cloud cover. I also wanted my analysis to cover a longer span of time, but I also wanted to maintain consistency and utilize Landsat 8 for both years. So since it was launched in 2013, the year 2014 was the earliest of years that I could use. So that's what I went for. And then the availability of high resolution imagery was extremely limited in the region. So I determined Landsat 8's 30-meter resolution was the best of other options that also was able to encompass the entirety of Tillaberi. So the 2 bar graphs show the percentages of either negative or positive NDVI change within 1 and 8 miles of each site, respectively, as well as the north and south subregions and the Tillaberi region as a whole. The Tillaberi region and subregions have similar values, averaging from about 10 to 15% for both negative and positive change. The northern sites remain, the northern sites, to include MGIS, Abala, the remaining refugee locations, as well as the IDP locations, and the southern sites of the 3 asylum locations. So at 1 mile buffer, 8 of the 15 northern sites show evidence of positive NDVI change. And then at 8 mile buffer, 8 of the 15 northern sites also showed evidence of positive NDVI change. In addition, the northern subregion NDVI change average has a 5% higher positive change than negative change. And then for the southern asylum sites, 2 out of the 3 sites show negative NDVI change within 1 mile, and all 3 sites show negative change within 8 miles. So what does this mean? The purpose of this project was to determine if changes to vegetation cover in areas nearby refugee, IDP, and asylum sites in the Tillaberi region were consistent with the regional trends that point towards desertification. But I found that the majority of northern sites, the areas surrounding these camps, in fact, showed positive NDVI changes within the 7-year span at both 1 and 8 mile distances from the sites, and were therefore inconsistent with desertification and land degradation trends. And then these findings suggest that the possibility of agricultural expansion at or around these sites, with the increased demand for food and resources to support the increasing populations of these sites. There's a multitude of reasons why an understanding of the driving factors behind the changing landscape in the region matters. There's already widespread food scarcity throughout the country, and the deficit will likely continue to increase over time. If agricultural expansion is in fact occurring nearby continually growing sites throughout the region, this process may not be sustainable in the long run, as populations will likely continue to grow in size, and desertification will likely to continue to degrade the northern landscape. Additionally, their evidence shows increased interaction between pastoralists and refugees could lead to potential conflict in competing over nearby resources. Pastoralists have resided in the region for many years, well before any of these camps were built, and many consider increasing populations and agricultural expansion as a threat to their livelihood. So these pastoralists increase animosity towards farmers, refugees, and the government that supports them could turn many toward aiding or joining nearby extremist groups, thus exacerbating violence within Niger. So the project served to gain a baseline understanding of the changing landscape within the Tilbury region, the potential relationship between refugee IDP and asylum seeker locations, and evidence of agricultural expansion in the recent past. Again, I used Landsat 8 imagery in both March 2014 and March 2021 to compare NDVI changes between both years throughout the region, as well as areas directly surrounding these people of concern sites. My analysis found that the majority of northern camps located in the arid part of the Sahel, especially prone to desertification, experienced, in fact, positive NDVI changes over the 7-year period. This is likely a result of the increased demand for food and resources as these camp populations continue to increase over time. And then given the aforementioned implications of all this, further research has to be done to gain just a better understanding of the driving forces behind these positive NDVI changes near northern sites, as well as the majority of negative NDVI changes near southern sites, which is not what I was expecting at all. This would in turn require higher resolution imagery, potential field studies and interviews to determine the processes and levels of sustainability of current cultivation methods nearby these camps, and perhaps additional data to explore correlations and other climatic or anthropogenic factors. So that concludes my presentation. Are there any questions?
Bridget, that was a great presentation, very sobering presentation. Does anybody have any questions? There's one there from Fritz. Can you see the chat? Sometimes it's easier just to stop sharing to be able to see.
Okay, good idea. Let's see. Oh, there we go. Okay. Interesting presentation on an important issue. You may have mentioned this and missed it, and I missed it, but what were the decisions that you made in selecting 1 and 8 mile buffers? Are these distances related to a specific factor? Not entirely. I started my analysis using a variety of different buffer sizes. So I went from 1, 2, 4, 8, 16, and then I just kept kind of going from there. And ultimately, just for the sake of simplifying my results, I decided to opt for 1 and 8 miles. Yeah, that was ultimately what I decided to do, just pick 2 of them and see what happened from there.
Any other questions? Yes, I'm just curious, and I know this is, you know, the situation isn't good in so many countries, but does results like you're showing influence the kind of, or eventually would influence the kind of aid they're getting, or what do you see changing anything in the future, if anything?
That's a really interesting question. Like, being in the military, we're just constantly focused on these violent extremist groups, and like, how can we support the country and the French mission down there to, you know, quell the violence. And I ultimately wanted to take a different approach entirely from like what I'm focused on in my everyday work. And it's like, okay, well now, like, can we like start looking at the long-term environmental issues that exist down there? And frankly, Beth, I don't have an answer for you right now.
Yeah.
But I would love to bring this to the attention of people who might be able to do some further research and try to enact some change down there.
I'm glad you're working on it. Any other questions? Well, to keep us moving along, Bridget, if you could put your email address in the chat, because there potentially are some questions that are being typed, that would be great. And then those can still come to you. And we'll move ahead since it is 12:40. So Cullen Williams-Fryer is next. And Cullen, if you want to share your screen and get started, go ahead when you're ready.
Okay, so you should be able to see, can you see the presentation?
Yes. Yep.
Cool. Okay. Well, before I get fully started, I should mention that like 2 days ago when I was practicing, my computer decided to spontaneously restart. So if it does that today, I promise I'll be right back. Just bear with me, but hopefully it doesn't. But with that being said, thanks for joining me. My name is Cullen Williams-Fryer. My advisor for this project was Dr. Fritz Kessler. And the title and topic of this capstone research is a spatiotemporal analysis of crime in Minneapolis before and after the murder of George Floyd. So in this presentation, I will give an overview of the topic, the research question, and the data used, and I will then review the methods and the results, and I'll finish with key takeaways, future implications, and leave time for questions. So my research question was inspired by reports that crime in Minneapolis had been increasing since 2020, and I wondered whether there could be any connection to the murder of George Floyd. So I hoped to address 3 questions. Has the frequency of crime within Minneapolis following the murder of George Floyd changed in comparison to the past 10 years? Have the spatiotemporal distributions of 3 violent crimes in Minneapolis following his murder changed? If so, how? And finally, how do different subsets of Minneapolis crime data perform when used to predict crime occurrence? So the crimes analyzed were murder, robbery, and assault. All crime data was pulled from the city of Minneapolis's data portal, which is updated daily with point data representing crime occurrence within the city of Minneapolis. To assess whether there may be any relationship between crime in Minneapolis and George Floyd's murder, I used a variety of data visualization and spatial analysis methods. The first portion of this presentation will cover the data visualizations, including line graphs and trend lines, minimum and maximum monthly crime counts, and calendar-style heat maps. These methods were selected to help me gain a deeper understanding of the data sets and their trends, their visible patterns, and their limitations. Then I'll move on to the spatial analyses, including animations of kernel densities, standard distance ellipses, mean and median locations, and an emerging hotspot analysis. These methods were selected due to their ability to create outputs that can indicate changes in geographic extents or clusters of point data over time. I also included 2 methods of forecasting crime data in this research to test Esri's ability to ingest point crime data and accurately predict crime occurrence. So for context, I've created this map that highlights key areas. It includes the downtown Minneapolis core, the University of Minnesota campus, the Lake Street corridor, the location of George Floyd's murder, and Minneapolis's neighborhood boundaries. The Lake Street corridor was a location of many protests and riots in the aftermath of the murder of George Floyd. I'd also like to acknowledge one significant limitation that was discovered throughout this research. Murder occurs so rarely that many of the murder-specific analyses in this research had too few data points for the methods to produce results that were usable and or significant. So to start, I created this trend line showing total crime count of murder, robbery, and assault over every year since 2010. As you can see, there was a slow increase in crime from 2010 to 2017, a sudden drop in 2018, then a dramatic increase into 2019 and 2020. The trend line shows a total of 2,163 crime incidences in 2021, but it's important to remember that this only represents crime data through August 5th, 2021. With that being said, this does represent an above average amount of crime to have occurred by that time of the year. Next, I created this line graph illustrating all 3 crimes with their own trend line. These trend lines revealed a strong seasonal pattern from 2010 to 2017, although aside from a slight increase in occurrence following 2020, murder did not seem to exhibit any clear patterns. So year after year, crime occurrence in Minneapolis would rise following the winter, peak in midsummer, then decrease into winter, before rising again and repeating the cycle. Following this from 2018 on, there was a period of less consistent crime occurrence, abandoning the seasonal pattern of 2010 to 2017. Shown here is the same line chart as the previous slide, but zoomed into 2017 and later. These line charts also seem to show that there was an increasing delta year over year when comparing the busiest crime month to the slowest. To dig deeper into this finding, I created this line chart that showed each year's maximum month of crime activity, the red line, as well as its minimum, the blue line. Importantly, between 2010 and 2016, the maximum monthly crime counts generally increased while the lowest months varied slightly but showed no general trend in either direction. I also noticed that July and August were the most active crime months, while February has consistently been the least active month. Shown here are the 5 data sets analyzed in this research. The subset pre-murder data set was constructed by mirroring the post-murder data set. So the post-murder crime data included 437 days of crime following George Floyd's murder. So this new subset pre-murder data set therefore included the 437 days leading up to his murder. In total, 5 time periods would be assessed in this study shown here. To help contextualize the amount of crime that each data set would be dealing with, I also created this table, which shows each of the data sets and their crime count breakdowns. I then created trend lines that showed each crime's year-over-year % change in crime rate. The results showed that for robbery and assault, the yearly crime count from 2010 to 2017 stayed relatively stable. Murder, however, went through more extreme changes in % change. This is due to the limitation I described earlier. Murder's small data set means that small changes in the murder counts can represent large values of % change. Then, following 2017, all 3 crimes show much more variation in % change. I then decided to compare the average monthly rate of occurrence of each crime from the subset pre-murder dataset to the post-murder dataset. Shown here, the average monthly rate of murder increased by 111%, robbery by 19%, and assault by 28%. While the pandemic may have had an effect on the occurrence of crime, it seems likely that the murder of George Floyd may have contributed to these increases. For calendar-style heat maps, murder did not have enough data to produce usable results, but robbery and assault did. Typically, crime is more likely to happen at night. However, I expected the increased crime activity after George Floyd's murder to result in a higher level of brazenness due to mob mentality, thus causing crime to be less concentrated in the evening hours and more dispersed throughout the day. This slide shows calendar heat maps for both robbery on top and assault on bottom, with each cell containing the percentage of each day's crime that occurred in that hour of the day. For both crimes, the heat maps from the all crime data, 2010 to 2018 data, pre-murder, and subset pre-murder data sets all show crimes being concentrated between midnight and 2 a.m., with the least crime happening between 4 a.m. and 12 p.m. However, the heat map from the post-murder data set shows a slight diffusion of crime throughout the day, with a slight increase in the amount during midday between 12 p.m. and 3 p.m. Based on these results, it does appear as if George Floyd's murder prompted a small shift in the temporal distribution of crime in Minneapolis. Due to the observed seasonality pattern crime had shown in Minneapolis, I decided to split the crime data into 12 seasons. 12 fall and winter and 12 spring-summer seasons were created. The fall and winter season centered on February and contained November through April data, and the spring-summer season centered on August and contained May through October data. George Floyd's murder occurred in the 11th spring-summer season, so I paid close attention to the results from the fall-winter 12 and spring-summer 12 seasons to see if his murder may have contributed to any changes in the criminal landscape. For murder, due to how few data points there were available, no animation was created. However, successful animations were created for robbery and assault. I anticipated that these animations would show consistent clustering around the downtown core, the University of Minnesota campus, and North Minneapolis, which are all areas that have historically had higher crime levels. In these animations, you will see 3 panes representing either robbery or assault as it progresses through either the fall and winter seasons or the spring and summer seasons. You can see the seasonal progression in a slider along the bottom. The left pane shows a kernel density estimation for that season and crime combination. The middle pane shows a standard distance ellipse and the mean geographic location. And the right pane shows how the median location is changing from each season to the next at a zoomed in scale. The median location path is color coordinated in a rainbow pattern, with red indicating the most recent movement and purple indicating the oldest. Here you can see that robbery's kernel density, mean location, and median location were all centered in the downtown core area of Minneapolis, with dense concentrations in North Minneapolis as well, although the downtown core had more activity. Then in robbery's fall and winter 12 season, the season following George Floyd's murder, there's a new dense spot located in the Lake Street corridor. And the mean and median locations are pulled to the southeast. Then in robbery's spring-summer 12 season, you can see that the influence George Floyd's murder had on robbery's spatial distribution is likely short-lived, as the median location is already heading back towards its typical location. Similar to robbery's animations, assault's kernel densities and mean and median locations were centered in downtown Minneapolis, with dense activity in North Minneapolis as well. Again, similar to robbery, following George Floyd's murder in the fall-winter 12 season, there was a new dense area of assault in the Lake Street corridor area, and the median location was pulled to the southeast towards the Lake Street corridor and the location of his murder. In contrast to robbery's behavior of returning back to the typical mean and median locations, assault's median location in the final season, spring-summer 12, appears to remain relatively stable, indicating that the impact George Floyd's murder had on the spatial distribution of assault is neither lessening nor increasing, excuse me. So the two forecasting methods used in this study are the exponential smoothing model, which according to Esri is appropriate for data that has moderate trends and strong seasonal behavior, and the random forest method, which is recommended for time series with complicated shapes and trends that are difficult to model with simple mathematical functions. Because both of these methods could be used for the data chosen for this research, I decided to run both models and compare the two in their ability to predict crime. So a space-time cube is created for each data set, and each space-time cube is then run through both of the forecasting models. The results of each forecast included a predicted count of how many of each crime would occur in each neighborhood of Minneapolis for the next month, as well as related attributes such as high and low 90% confidence intervals and RMSE values. After a month had passed, the actual crime data was collected, organized by neighborhood, and compared to the forecasted crime values. I calculated an average percent error metric for each data set's forecast based on the error of each neighborhood's prediction. Because these forecast tools output predictions in non-integer values, I needed to round the forecast to the nearest integer and compare the true crime outcomes to that number. Therefore, another measure of accuracy was percent of actual neighborhood crime counts that matched the rounded forecast value. At the broader level, it was most useful to look at how each method performed when considering all three crime types combined. This table contains a summary of these accuracy results. When looking at minimizing average percent error, the random forest model outperformed the exponential smoothing model 4 times out of 5. The percentages on the right side of this table represent what percentage of neighborhoods had a rounded forecasted value that matched their true crime value. While the exponential smoothing method did outperform the random forest model 5 times out of 5, it's important to note that it outperformed the random forest model by an average of just 1.61%. Because this represents a small increase in accuracy, and considering the random forest ability to minimize the average percent error, a key takeaway here was that the random forest model would be a reasonable choice for future crime forecasting work. While working with this forecast data, I also analyzed the RMSE values produced with the forecast, which allowed me to analyze the model's confidence in its own predictions. Plots were created that included a set of 3 points for each neighborhood, one for the forecasted value, one for the RMSE value associated with the forecasted value, and one for its true crime value. In addition, confidence interval bars above and below the forecasted point were included that represent its 90% confidence interval. The output shown here contains surprising results. As the forecasted number of crimes increased, so too did the RMSE value. The higher the number of crimes that was forecasted, the less stable the model performed. Future research that intends to use these forecasting tools should be aware of this limitation and should ensure that the outputs contain acceptable RMSE values. 5 emerging hotspot analyses were computing using all 3 crime types. According to Esri, a hotspot is classified as a cell with a high value that is also surrounded by high values, relatively speaking, and a cold spot is where the inverse happens. A cell with a low value is surrounded by low values. Shown here are the results. It's important to note that each of the hotspot types shown in the legend of this image are present in at least one of the map panels shown. When comparing the subset pre-murder dataset's output to that of the post-murder dataset, there are new hotspots classified as sporadic hotspots, which are sometimes statistically significant hotspots and sometimes not, according to Esri, which are located in the area where the riots and protests were. This confirms my original assumption that there would be new hotspots in this part of Minneapolis. Furthermore, the output from the post-murder dataset shows a new cold spot in the northeast area of Minneapolis. I'd expected that there would be new cold spots in areas that previously had higher amounts of crime. However, this new cold spot was not in an area that is known for criminal activity in the northeastern area of Minneapolis. Therefore, this doesn't necessarily confirm my theory. However, it's possible that the underlying logic applies that the area identified as a new cold spot may not have been a statistically significant hotspot before, but that it did see a decrease in crime due to the fluctuation in crime's spatial distribution following George Floyd's murder. One final comparison of kernel density estimations was created using a kernel density from the subset pre-murder dataset and a post-murder kernel density shown here. Notably, the density output from the post-murder data is much more spread out than the output from the subset pre-murder data, and the downtown core of Minneapolis is much less active in the post-murder data set. While the Lake Street corridor does have denser amounts of activity, excuse me, post-murder, it also appears that North Minneapolis, the University of Minnesota, and other neighborhoods are also denser. As was seen through the animations, the impact of George Floyd's murder was likely short-lived, as those locations are seemingly bouncing back to their previous locations. However, it's important to acknowledge that George Floyd's murder was such a socially stimulating event that crime increased in certain areas of Minneapolis where it otherwise likely wouldn't have. Overall, George Floyd's murder likely contributed to an increase in the average monthly rate of occurrence for all three crimes, a slight increase in crime activity in early afternoon hours of the day, the spatial distributions of robbery and assault shifting to the southeast, although robbery has already begun returning to its typical location from before, new hotspots of crime in the Lake Street corridor while also causing new cold spots to appear elsewhere in the city, and an increase in crime count while it simultaneously propagated in numerous spots throughout the city rather than in just one or two. In regards to forecasting, I found that the all crime data set performed best in regards to average percent error, while the 2010 to 2018 data set had the highest number of neighborhoods match their rounded forecasted values. Between the two forecasting methods, the random forest method produced the best overall forecasting values. Future iterations of this work should include other types of crime. Alternatively, this same analysis could be run in different cities of equal population size to compare findings. Similar work in this area should take care when analyzing murder, as it occurs sparingly enough that smaller data sets often lead to results that are easily skewed or unusable. Finally, I'd like to express deep appreciation for Dr. Fritz Kessler. He was a tremendous support throughout this process, had a lot of great recommendations, and was also always asking really great questions to sort of prompt deeper thinking. So with that, does anybody have any questions? And I will stop sharing.
Thanks, Colin. Speaking of great questions, does anybody have any questions? Presentation.
So Marcel said, you probably mentioned this and I missed it, but which tools did you use for forecasting and to create the animations? So for forecasting, Esri has a toolbox within ArcGIS Pro that is specifically for time series forecasting. And so the methods I selected were the random forest method as well as the exponential smoothing method. They have a variety of methods. The other, I think if I remember correctly, there was 5 that you could use for the forecasting, and the 2 that I selected were the most applicable to the data based on its sort of its trends and its how it was laid out. And then to create the animations, I originally wanted to use Pro as well to create the animations, but because there's functionality within Pro to create animations, but I started to use it on my computer like basically lit on fire. It just couldn't handle the process, and so I ended up I exported all different frames to a JPEG and then stitched them together into animations just through a free website. Greg said, were you able to control for other things that might have impacted the crime rate around this time? For example, the pandemic or maybe changes in police standards. So that's a great question. And that's actually one of the biggest limitations of this research was that the pandemic was also going on at the same time. And so it's really hard to, if not, at this point in time, it's really hard, if not impossible, to compartmentalize the effect that the pandemic may have had on crime with the effect that George Floyd's murder may have had on crime. And I do call that out multiple times in the paper for sure. And I think I mentioned it hopefully at least once in this presentation. And then regarding the changes in police standards, that is something that I also gave a lot of thought to and kept an eye on the news. I have family in Minneapolis, and so I'm sort of tuned into like what they're proposing with police standards and what the police force has been doing. And as of yet, if I understand the situation correctly, there hasn't been changes to the standards themselves. There's been some changes to the police force, but nothing in terms of their response to crimes. Hopefully that answered your question.
Great job. Yeah, I was sort of thinking the same thing. I was looking to see where you were living. I'm like, oh yeah, California, but that makes sense. You have some family there, and I'm sure, yeah, just like me here in Pennsylvania, I was looking to see, did any of that legislation they were talking about actually go through or anything like that. So it's still pretty, you can kind of get a handle on what's going on a little bit. from
Mhm.
afar.
Yeah, yeah.
Well, very useful and important presentation. And who knows, maybe you can, let's hope the pandemic is over soon and you can throw in a couple more years of data sometime down the road.
Yeah, for sure.
Okay, so we are right on track. So Michael Aguilera is up next. And so Michael, whenever you want to start sharing, and you can go ahead.
Can you see my screen now?
Not yet. Oh, it looks like it's coming up. There we go. Yep, we can see it.
Okay, perfect. Hi, so yeah, my name is Michael Aguilera. My project for my capstone was studying urban growth impacts on HCA or high consequence area and class location changes using orthoimagery and LiDAR data collection. So a little bit about myself. I work for Pacific Gas and Electric out here in California as a GIS analyst and a gas program manager. So this study is pretty important to us on a year-by-year basis, and hoping some of the results of this will kind of go on a quarterly basis and try to reduce the risk that we can to our gas transmission pipeline system. So give a quick intro, the goals and objectives, and then methodology I use, and some of the analysis and results, and some ongoing work that I've made, some dashboards and for other groups, and then some future goals that I have. So yeah, quick background. So with a lot of rapid expansion in some of the cities within the Bay Area and throughout Northern California, there's a lot more housing developments being built, apartment buildings, the need for increase in housing with the demand of some of the jobs in, per se, like South Bay and San Jose area. This also affects the risk that now there's more structures near our gas transmission system. So there's more threats and the need to continuously make sure that we maintain our pipeline system to lessen the threats on the public and safety for everyone. So yeah, pipeline integrity and risk management. This is a critical study for that. Change detection, we're able to see in some of the wildfire areas that we've had in the past 5 years, areas where homes were destroyed and seeing homes being built back, we're able to monitor that with this LiDAR collection. And then, yeah, I'll get into talking about high consequence areas and classification real quick, because I know that's not something everyone may be aware of. So class location. So a class location is basically a unit, is an area that extends roughly 200 meters on either side of the center line, which would be the transmission pipeline of any continuous mile. And so there's 4 different classes that are listed by PHMSA that we use. So class 1 is basically any dwellings or basically residential homes, 10 or less within this area. And then class 2 is 20 or less. Class 3 is roughly, I think, basically 50. And then class 4 is basically any homes that were also schools, apartment buildings, big office buildings, parks, which also can go back and forth between class 3 and 4, for example. So basically any place of a common gathering where more than 20 people gather there for at least 5 days a week. So obviously like a school, people are going there every day of the week. I know last year was kind of weird with COVID, but we still would leave those as a class 4 structure, knowing that eventually as things have slowly gone back to normal, kids are going back to school in person. So yeah, what is an HCA? So a high consequence area. So right here in the potential impact radius that you can see, that's basically the high consequence area. So we call the PIR buffer the potential impact radius, which basically is the extent of the pipeline, which depends on the contents that's running through pipeline and what pressure the gas is flowing at. through this area. And it's 660 feet on either side of the pipe. And then so the structures that are within the PIR buffer, high consequence area, would be homes that are listed as an HCA structure. So we're aware of how many homes or buildings that are within this buffer, and the segment of pipeline would be classified as an HCA. So this pipeline would definitely get more attention to with maintenance, and since it's a threat to more homes per se than the homes to the back or different parts of the system. And then this chart, this is the chart we kind of just use. I know it's from PHMSA, and it's kind of just how we know that there's continuous change with our HCA, that the need to constantly do this to reduce threats and risk. And if there's any remediation and assessment that pipe we can maybe move to a different location where we know homes wouldn't be built or any structures wouldn't be built to lessen the threat to the public. Moving along. So here's some examples, a little bit of background before I get into results. So the Santa Rosa fire that happened, Sonoma fires that happened in 2017 kind of unfortunately destroyed a good section of neighborhood in Santa Rosa. And for us, as you can see, the HCA segment that runs along 101, we can see that the homes, that were destroyed in this area, but we're able to monitor year by year to see that, they were slowly being built back. So in 2018, you can see some homes have been built back. Not everything is coming back to normal, but as over time, yeah, sorry, this ortho imagery wasn't the greatest for this year, but for 2019. But yeah, you can see more homes are being built. There's still some open parcels. And then by 2020, you can see we're able to monitor that things have gone back to normal. So we're able to keep monitoring the situation and unfortunate events that happen within our system. And then, yeah, and then it's good for us to know in this location, the reason I chose this, that red little structure that's highlighted below all the yellow polygons is a care facility. So before this home was gone, and we need to know where care facilities are at, even though most of these homes will just be classified as a class 1 or 2 structure. But this care facility would be an HCA structure because since there's medical attention there, and it's close enough to the pipe where we need to know. And then kind of an interesting thing, I threw this in here with the pandemic. It was kind of interesting to see, obviously, nearby structures that were already existing HCA structures, like this Soul Cycle spin class, that there's an outdoor area. So although that will probably go away, I would think in the next year or so, and we could remove that out of our database. But it's interesting to know that we picked up more structures. Maybe they weren't actually physical new buildings, but these pop-up tents just to, as people were adjusting to the pandemic during the height of it in 2020. And then to the one to the right with the outdoor tents, the church next to it, which isn't shown in this photo, was already classified as an HCA structure, but it's good for us to know that there's a couple more areas that we should be aware of within that parcel that could be a threat to maybe not a threat obviously to the pipe, but our pipe system would be a threat to people maybe gathering there either during the week or on weekends. So some of the goals and objectives. So yeah, the main one was determining the changes, class location HCA changes from 2015 to 2020 in the Bay Area. And the next slide, I'll show how the counties listed with the HCA segments. And then for myself, and then some of the organizations I work for or work along with, we can see that some of the urban growth impacts of people moving away from the Bay Area or moving back to the Bay Area with new apartment buildings being built per se, shopping centers, that there's more threats that could potentially impact our transmission system. So this was my study area. So Bay Area region. So the reason I called the Bay Area region is I know some of the counties like Sonoma and Napa are technically like wine country and going into North Bay. PG&E classifies this area. We have 5 different regions, and this is the one that's called the Bay Area region. So that's why it's listed as that. So as you can see, there's Marin, Sonoma, Napa, Solano, Contra Costa, Alameda, Santa Clara, San Mateo, and San Francisco counties. And then the blue lines that you can see within each county in this area are the HCA pipeline segments of our transmission system that are currently defined as HCA. So moving along to the methodology. So yeah, there's a couple, 3 workflows in this. So creating the orthoimagery from our LiDAR collection, processing, and generating the point clouds, and then to help create the orthoimagery. And then in this middle section, which leads back up here. So yeah, we'll identify the HCA. So there's a lot of scripts we run, risk rankings that we'll do with the buildings that the building captures that we get as well. And we'll update those a county by county basis. So there's a team of myself and a few others will go in and classify each structure properly. And then with doing this study, we'll also look at the previous year's collection, obviously the county boundaries, and then we have a care facility layer, since it's critical for us to know how many care facilities are within our HCA segments pipe, and if some of those have changed or if more have been added. And we've noticed a trend of more care facilities being added. So yeah, that will help us review the current structure layer. We'll update key fields. So the type of building, how many people are approximately there. So sometimes we'll have to call the actual physical building to get an idea, especially for like an office, because some offices, I know there's a lot of open spaces for lease, but we're able to call customers like that and get the actual counts. And then, so yeah, once that's review of the structures is done, we'll upload that into the final structure layer, and then we'll document new HCAs, and then we'll classify. And then that gets uploaded into our master database, and then we're able to create maps. Now we're trying to create more web applications and dashboards, since that's a better trend. So some of the analysis and results, I'll try to go through these quickly since I know I have a lot to go through, but short on time. So yeah, so you can kind of see a trend. So a lot of the structures kind of follow, obviously, where HCA pipeline changes have happened over the years. So Alameda, I'll go to this one. So Contra Costa, kind of interesting in some locations where along here, as you can see, a cluster up here in the Richmond area, in this part of the bay. So some segments being classified as HCA now has pushed the structures to be classified as an HCA structure. There's a lot of new buildings being built near, it would be Interstate 80 and shopping centers. So it's kind of interesting to see the trend of more areas being developed, and the changes with pipe kind of coincide in some of the areas over time. So yeah, Marin, this is actually interesting as well. So sometimes when there's heavy rains and flooding, some of these highways can get flooded. So now we've defined some of the highways, because we've moved some pipe above ground along the highway. So the parts of 101 are defined as an HCA area. And then, yeah, so you can kind of see a trend with Napa. Not too many changes here. I guess one thing to note out, the numbers in parentheses that you can see on the HCA structures. That's just the increase of the number of HCA structures that were defined that year. So there's been a trend upwards in each of these counties. Let's move along. Yeah, so here's another good one in Santa Clara County, predominantly in the San Jose area, in Cupertino, in Sunnyvale. There's a lot more office space being built along the various highways and expressways in this area. So it's interesting to see the trend. We're able to monitor this over time. And then Solano County, interesting enough, some of HCA areas have already been defined previously before 2015, and there's some more in these yellow clusters. In 2019, there's more housing developments being built out here where there's more open space. That's also, for us, we need to be aware of that since it's already along previous pipe segments. So there's kind of doesn't seem like there's a correlation, but if I had like previous from 2015 and before, it would make a little bit more sense. And then, yeah, and here's Sonoma. So I'll move along to closing thoughts to wrap this up. So yeah, working with upper management and some other groups, we're able to create web apps and maps of the HCA class location layers on a year-by-year basis. We're able to show changes so even field crews can see this, create a feature service, and we're able to observe signs of urban growth and development affecting the changes over time. And it's impacted how we need to think, even our critical thinking of how we should be maintaining these segments of pipe in certain areas and increase the frequency of surveys in these areas. So we're staying on top of reducing risk, keeping the public safe. Some ongoing work that I've done, I'll show you real quick. So this is for our pipeline patrol teams. So they survey the system twice or once a month, and then they'll do the HCA as well. So they try to do this every month. So this bottom one, the second pass flight, would be our HCA segment. So it's kind of neat. We're able to upload this data and give them the accurate data so they can use this to fly each of these areas that they defined. So they're able to patrol this, and we can see this, and other groups can see what's been patrolled on a month-by-month basis. So this helps for upper management to see. And then lastly, before I wrap this up, so here's another example of using the web apps. And then, so for here, you can see that our ground patrol team now has access to some observations that we can see along this HCA segment that runs right here, that there's homes being built up right along this pipe segment. So it's good for us to be aware of that in the future, that we'll see structures pop up. Obviously, they might not be an HCA structure, but it's just more buildings that are defined as class 1 or 2 that are right next to this pipe segment. And then, yeah, future goals to create more user-friendly applications to display up-to-date changes, and then an application where crews can just update on the fly to keep everything updated. And yeah, with that, that concludes my presentation. So any questions or comments? And then I'd like to also thank Pat Kennelly for his advice throughout this whole process. It's been great. It's also been great to get into him as well. So, thanks.
Great job, Michael. Thanks for the presentation. Does anybody have any questions? There's a question in the chat there for you.
Oh, see it now. Okay. Something personally I learned from this project. Yeah, I think it's personally, I know there's just so much risk in like everything to monitor. It's crazy how there's so many, like, I never knew there were so many care facilities in some of these counties, in so many areas. So it's kind of interesting to know that, but it's also important that we need to be aware of those. And then I guess I know we always work with construction crews continuously, making sure they have the right permits to build, but it's crazy. A lot of things are just being built right along freeways now, so it's just more of an impact to us. But it helps, drives us forward to keep moving along to keep the public safe. Because I know PG&E doesn't have the best past history, and I know we're trying to move forward and get better. And also, it would be interesting to do this study in the future for the Sacramento area, since there's a lot more new developments being built there.
Great, thank you. Since we're right at 1:20, maybe Michael, you could put your email in the chat so that anybody else can send you some questions. And we have 2 more presentations today.
Thank you.
Greg Cook, yeah, thank you. Greg Cook is next, and then Katie Sear. Jim Dow is going to take over for me in a little bit here because I have to go to Faculty Senate. So I will get to see some of your presentation, Greg, but good luck to both of you. And Greg, whenever you're ready, you can go ahead and start.
Can everybody see my screen and hear me?
Yes.
Okay. So I'm Greg Cook. This is a presentation of my capstone, an examination of county level suicide mortality in the US. I'm interested in if there's a protective effect of environmental lithium on the suicide rate. I just want to say thank you to my advisor, Professor Stephen Matthews, for his support and guidance throughout this project. It was a very intensive process. So just to review, lithium is geographically varied in the environment and across the US. It's considered toxic in large doses when consumed. But it's also used as a medication actively. And lithium has been used as a medication for bipolar disorder and major depression for a very long time. Has a strong anti-suicidal effect. And then suicide is a growing and changing trend in the US, where it's increasing as a cause of death, and it impacts different populations within the US very differently. This is just a slide reviewing the geography of lithium. As you can see, it's spatially varied across the U.S. Big points are the Atlantic coastline for very low levels. You can see the impact of glaciation in Michigan and Wisconsin and so forth as well for very low levels of lithium. But you can also see very high levels like the Northern Rocky Mountains and the Appalachian Mountain region. And this slide is just an overview of the geography of suicide again, that it's overall seen an increase since '99. It varies quite a bit by population within the United States. So by age and sex, race and ethnicity, it varies. There's some areas which are very high in the US, like Native American reservations, and it's continuing to change over time. So one of the things from the research presentation I had was we weren't quite sure what project to do. So we discussed doing a couple of different variations of across the whole of the continental US versus a specific state region, or a transect of some portion of the US. All the existing research is largely state by state. And it's all focused on water quality data sets, all of which is aggregated to a county level. So what we ended up doing was we looked at 3 different data sets, lithium data sets. So 2, the National Geochemical Database and the USGS Data Series 801 release are soil quality data sets, which is have not been used previously in research, and the National Water Quality Assessment Project dataset, which is a water quality dataset, which water quality datasets have been used in existing research. There was an existing study in Texas by a group headed by a guy named Blumel, that we used the demographic control model from to try to assess the impact of these demographic variables on the suicide rate. And then we ended up analyzing this whole process with a GWR model through MGWR. So this is a little bit innovative. There hasn't been a national scale examination of this effect in the continental United States. Previous studies haven't looked at these different lithium sources. And there's only limited use of GWR as a modeling technique to analyze this effect. So this slide is a map of the suicide rate in the US. So this is the CDC Wonder data for suicide from 2010 to 2019. As you can see, suicide also spatially varies quite a bit. You can see, it's very high in the West, but there's also issues with MALP in the West. There's very few areas in the country where suicide is at or below that average level. So there's a lot of things where, that average level is driving things. This slide covers the data that we used from the model. So the time spans for the data were all aligned to try to have demographic variables collected after the lithium data sources. The assumption being that lithium data sources would be a more static value than the demographic data. So there's a number of issues with the data sources. No data set had complete spatial coverage of the United States. There's suppressed data issues in both the CDC Wonder and the American Community Survey data sets. There's something called a limit of detection issue in the National Geochemical Database data set, where they provide samples where they aren't entirely sure of what the exact value is. So they give you what's essentially an upper limit. And then the lithium sample data sets that we had aren't in the same scale. So the National Water Quality data set is in micrograms per liter, and the soil data sets are in milligrams per kilogram. And there's about an order of magnitude difference there. It's also kind of unclear how these environmental lithium levels relate to people's actual consumption of lithium, because that's what's really driving these impacts is people having access to lithium some way through the environment. So there's an existing body of research that shows that there's some impact here, that environmental concentrations are a protective effect on the suicide rate and reducing it slightly. I wasn't entirely sure what was going to happen, but we assumed that we'd be able to replicate this at least globally, likely with the National Water Quality data set, since that's similar to the existing research. We weren't sure what would happen with local models with the GWR, but assumed that there would be some relationship shown there as well. One thing, two things I was also interested in are the existing research shows there's a stronger association between male suicide and these environmental concentrations of lithium. And there's also some theory to a threshold effect. So there might be levels environmentally that are high enough that you reach a threshold for this protective effect. So this slide covers the actual model runs that I generated. So things that are highlighted in gray are model runs that included demographic variables for control. And things that were highlighted in white do not include those. So it's lithium only in the items that are in white. As you can see here, the only statistically significant model run that included demographic control was this NACWA 02 run globally. So that corresponds to the National Water Quality Project data set. And there wasn't significant results when controlling for demographic variables in the soil data sets globally. Also, it's unsurprising that the lithium-only models were found to be statistically significant. But if I can go back, sorry, I'll go back and show that again. It's unsurprising that the lithium-only model runs were statistically significant, but as you can see, their R2 values are very, very low. So there are, in the next slide, I can show there are local areas of significance that differ from this global model, and the fit locally differs quite a bit between the global and the local models. The R2 is only about 44–45% globally at the highest, but it gets much better locally in the GWR model. I can show this here. So this is the local R2 fit within the actual data sets, and it gets much, much higher, particularly along the coastlines in California and the East Coast, but much lower in areas in the West. And see there's substantial portions of data sets still missing here in the West, where it's low levels of population. So this slide shows the specific OLS model results for that NACWA 02 model run. So you can see over here the p-values that population density, unemployment rate, percent Black or African American, percent Hispanic or Latino, and median household income, as well as the lithium samples, are the statistically significant variables in this model that are driving it. And then this map is basically the key outcome from the work. This compares the local areas of significance out of the GWR models for each of the local runs where demographic variables are controlled. And it shows that there's some overlap in the West, particularly like this region in Southern California, where you can see is gray. There's overlap between all three of the data sets there. Largely this, to improve this, it needs more data points. So a lot of this is, areas where we're missing additional data. I guess I should point out with this too, this is coded, so it's only showing the areas above or below statistical significance. So areas that are lighter have negative statistical significance, and areas that are darker have positive statistical significance. And then when they overlap in areas are more gray is where they overlap. So again, this is the local model fit. So it's showing it's much higher in a local model fit than in the global model fit. We can show you this. This is from the USGS data series 801 soil data set, and it's the most complete data set. And it gives you the best picture of how well fit this model is. So there's many things that could be done in the future. The USGS data series 801 release has geochemical information on a huge number of elements. So specific things that might be interesting to look at would be like arsenic, mercury, thallium, or lead, all chemicals that have a pretty clear impact on human health. it would be interesting to figure out if there's a clearer connection between an impact of lithium with doses that are much lower than therapeutic levels. Is the highest or the lowest therapeutic level I could find documentation on was about 150 milligrams a day, which is much higher than somebody would be able to consume, even in some of these regions with very high levels of lithium. There's one of the things we did was aggregate to the county level. An alternative aggregation boundary would be health service areas, which are used in a lot of health research. There's also plenty of opportunities for larger scale analysis. Everything, and this was done at the county level. Potentially you could do something at the census tract level, which would be interesting to see if this effect still holds true. And there's areas in the country where you could do this. In Colorado has data available at this level. And then there's a project called the 500 Cities Project, which has census tract data available for the 500 largest cities in the US. In terms of statistical technique, this could probably be improved by analyzing either using multi-scale GWR or semi-parametric GWR. At least some of the variables in this model appear to be globally significant. So particularly semi-parametric GWR might be a useful analytic technique because of that. We've been talking about seeking publication for this, so I'm working on formatting a version of my thesis for publication for Science of the Total Environment. These three journals, Science of the Total Environment, International Journal of Health Geographics, and Crisis, they're all journals which have some existing similar work and may have papers already published that are related. So Science of the Total Environment particularly has a paper in 2020 by a guy from the USGS named Bruce Lindsay, who did a much larger national analysis of lithium in the groundwater in the US. So any questions, comments?
All right, thank you, Greg. Nice work. Great to see that you're thinking about publishing this work. So yeah, are there any questions for Greg? I have a question if there aren't any others, and I apologize if I missed this, wasn't paying close enough attention, but it's unclear to me how lithium gets into the environment and then how it gets taken up into people's bodies. Maybe you could talk about that briefly.
There's environmental distribution, so it differs largely based on the underlying geology. I talked about it more in the research presentation. The reason why I think the existing research has focused on water consumption, water quality data sets, is because people are actually obtaining lithium through their drinking water. The USGS and the EPA, their standards for what they consider toxic amounts in drinking water are all based on access to that water source, basically. So there's a higher level of lithium consumption that you can would be considered toxic if you only had access to drinking water, for example. So I think that's considered the primary driver in this effect of people consuming lithium through water.
Gotcha. Yeah, that's helpful. Thank you. Other questions for Greg? Well, I'll ask another one. Do you see any kinds of policy implications around your findings?
The one I've been concerned about, I think somebody who knows more about how the EPA works is probably would know a lot better. Is just this year in March, the EPA added lithium and a whole host of other chemicals to what they call like there's a monitoring rule where they can force local local water quality agencies and water treatment plants to report to them if these chemical levels are out of bounds what they expect. And lithium at least will be reported now. I've wondered a bit if that would be a pathway to regulation, and if so, I think it has some concerns that if it was regulated, we'd want to watch the suicide rate in areas where it would get regulated to see if there was a change there over time during regulation. But I think it's a question of is that the EPA's actual path, or is it just monitoring for being able to inform people that this is occurring?
Okay. Yeah, thank you. Nice job answering my questions, and best of luck getting your work published.
Thank you.
So that brings us to Katie Sear, our last presentation of the day. Katie, are you all set to share?
Yes.
All right.
Can everyone see my screen?
Yeah, I can see your slides, and take it away.
So good afternoon, everyone. My name is Katie Sear, and I'll be talking with you today on my project for planning and implementing a GIS-based asset management system for stormwater pipes. So to start, I'd like to thank my advisor, Professor Steiner, for his guidance throughout this process. So my project follows the city of Fort Worth in a model of a shift from a proactive to reactive approach for managing stormwater pipes. So a reactive approach follows a general flow as shown on the left. Something breaks, and in this case, there's a cave-in, and then an emergency repair is required. This, of course, can be minor or major in range and cost based on many factors like the location, the size of the pipe, and the cave-in, and so on. So a proactive approach, which I plan to model, will follow an extended process flow, which would help to better plan and make asset-based decisions rather than emergency-based decisions that we typically find in that reactive style approach. So asset management is just defined as a continuous process that guides the acquisition, use, and disposal of infrastructure assets to optimize service delivery and minimize costs over an asset's entire life. So common examples of infrastructure-related assets are manholes, inlets, and pipes. And then, of course, this concept also extends to other non-infrastructure areas like IT or other non-physical assets, like a series of companies, for example. So the typical practice of asset management can be simple or complex, but generally it follows a cycle that provides the owners or managers more information and tools to make data-driven decisions. This helps to maximize use of funds and, from an infrastructure standpoint, achieve sustainable infrastructure goals. So what is a stormwater system? A stormwater system is a network that conveys water runoff and is comprised of assets such as pipes, manholes, inlets, and channels, for example. So a stormwater system can be a separate network on their own, or it can be combined with water and or sewer networks depending on the city or the location. So for the case of the city of Fort Worth stormwater system, it's actually a separate network from our water and sewer systems. So Fort Worth stormwater network has a little over 997 miles of stormwater pipes, a little over 27,000 inlets, and over 7,000 manholes, just to kind of name a few different asset types and set that general scale related to the stormwater infrastructure for the city. And of course, these assets are all either owned or maintained by the city. So cave-in or sinkhole is defined as the collapse in ground surface. So they're common across the United States. States with the highest number of sinkholes are Florida, Texas, Alabama, and Kentucky, just to kind of name a few. Cave-ins or sinkholes, of course, can be caused by natural occurrences, such as the photo on the left of a cave-in or sinkhole that occurred in Florida. And then we have that map on the right from USGS, which shows some of these areas that may be more prone to sinkholes or cave-ins based on their surface geology. And cave-ins or sinkholes can also occur from a human element, such as urban infrastructure, like pipes, or a combination of that natural human element. These, of course, occur in areas of heavy rainfall, urban areas with underground infrastructure, such as sewer and stormwater pipes, or in areas with limestone karst subsurface. We can also see cave-ins or sinkholes occur in waves surrounding severe extreme weather. A more recent example for Fort Worth that some of you might have heard a little bit about in the news was related to the extreme snowstorm which hit Fort Worth in Texas early in the year. So this storm resulted through somewhere around 720 and then somewhere around 900 street repairs, a number of which resulted in cave-ins or were repaired as a preventative measure. So for the urban element, this is something that can be as minor as the image on the right or more severe as the middle and left images. So the first image on the left engulfs an entire three-way intersection and involves a water pipe infrastructure. The center image was estimated to be a 20-foot by 12-foot sinkhole at the surface and was caused by a stormwater pipe collapse from heavy rainfall. The image on the right is a small early stages of a sinkhole in the roadway. There's a small hole with the surrounding area beginning to sink, and at this stage, the site is being evaluated and the cause is undetermined. So why is this important? This is important because these scenarios are unpredictable and can both be hazardous and costly. A cave-in or sinkhole can happen at any point and addressed as the issue occurs. Whereas a proactive approach has advantages of identifying faults before an emergency may happen. This image in the center shows an intrusion of an unknown utility pipe through a stormwater pipe. The map on the right is actually showing the aerial view of the area. That dashed yellow line you see is the part of the pipe in between each manhole and is associated with that CCTV image in the center. So as we can see from these images, this is a geospatial problem unseen from the street view. So these are images, which are a series of paper work order tracking, along with several stacks of work history, which are unfortunately in most cases are left stacked on desk or filed into cabinets likely to never be found again. And then a series of paper maps and map books which reference an outdated map scope. This example or similar can be found in some form or fashion across many entities. And this, of course, is not an example of best practices. So the focus of the project methods are around the, oops, I think I got one too far. Go. So the focus of the methods are around the design and users, but it's important to note that there are other aspects, such as a full GIS inventory collection, data quality control, and assurance, and process implementation that sets the foundational aspects. So for the case of the city of Fort Worth, Stormwater, they worked with a consultant to develop their database design collection and data QA/QC. Underground asset infrastructure was mapped from plans and professional field surveys and continues to be maintained this way. So my project goals were to analyze and compare an associated pipe repair and complete a general comparison of emergency versus routine repair as it relates to the repair time. So with these results, a training field manual draft and model of typical business process flow is developed. So stormwater pipes can have various levels of accumulation of organic and non-organic matter like rocks, leaves, trash, and building materials, which can be washed into stormwater pipe network through culverts and inlets. We see an example of this in the photo on the left. Debris such as this at varying levels can prevent a successful CCTV or cause damage or loss of CCTV equipment. So an initial pre-CCTV pilot was conducted and manually tracked as shown in these images. So data was extracted through a GIS from a series of definition and spatial queries and provided the field teams through spreadsheets. Pre-CCTV checks conducted by field inspectors determine if a pipe is ready for CCTV. If during visual inspections, a pipe is found to have debris, an inspector will flag the pipe for cleaning. The list of pipes that need to be cleaned are then transferred to a pipe cleaning crew who will conduct cleaning shortly after. So this process morphed into a more formal digital process after several field iterations. The image on the center and right shows the digital tracking form as well as the digital maps used in the field. So the primary GIS inventory and assets required for this process are pipes as well as manholes, which act as the entry and access points to the pipes. In some rare cases, inlets can also act as access points as well. The fields as shown on the left are the minimal attributes that would be required for the data. Most of this data can be found on engineering plats and plans or can be collected during formal field surveys. The attributes recommended for collection during CCTV are shown in the left table. These would be a unique ID that could tie to the asset, inspection date, observation, video link, and pipe attributes to verify against the main asset layers, just to name a few. This information is made available in digital form through map services. This provides opportunities for the field teams to better manage their work within the field and access real-time information. This digital approach also supports long-term goals of data and asset management, as well as provides a mechanism for performance goals for field teams. So the map on the left shows a pipe cave-in which occurred off West 7th Street in Fort Worth and was the focus of the model shown in the next slide. So for those not familiar with this area, this is a heavily trafficked neighborhood with a large shopping area and homes and apartment complexes just across the street. This street is about a half mile or less from our downtown and is a main corridor. So a React approach as modeled on the left, again, something breaks and creates a sinkhole or cave-in, an emergency replacement is required. A proactive approach as modeled on the right can be something that's planned and prioritized. So using data samples from a similar pipe material and diameter and employee cost averages, the model shows the estimated differences in employee hours and cost per linear foot of pipe. The estimated results showed a higher cost for a replacement, so a reactive approach compared to a proactive planned replacement. Also with the estimated reduced level of repair, a proactive approach also has some sort of assumed reduced level of potential risk of safety to citizens, field teams, and then emergency responders. So the final high-level proactive process flow as modeled on the slide follows the beginning stages of an asset. So an asset is drawn in GIS from plans and remains in the GIS inventory. A pre-CCTV check is conducted to determine if a pipe is ready for CCTV. CCTV is then conducted. The pipe is either evaluated on site or later reviewed by a field engineering team or both. And then pipe repairs are prioritized and planned, and a pipe replacement starts the asset life cycle over again. So in addition to the primary project deliverables, an additional analysis was conducted using citizen reports of potholes to create a density map overlaid with cave-in calls. The results show some correlation between reports of potholes and reports of cave-ins, primarily through the center portion of the city, which is shown in this map. So field verifications would need to be conducted to kind of solidify the analysis results. But with these results in mind, a prioritization mechanism or some other output that provides a means to make data-driven decisions through geospatial patterns could occur with this. So there are several lessons learned throughout the life cycle of this project. First is the importance of the foundational aspects of GIS best practices. An analysis of staff requirements for data upkeep and data entry processes play a significant role related to the data in this project. Without a solid foundation of each, it's easy to see how quickly delays can be caused in a pipe CCTV program. Additionally, it's important to address how GIS data inaccuracies found in the field should be collected, addressed, and then corrected. So in the event the pipe or access point information is found to be incorrect in the field, how does that information get relayed to the appropriate group for data corrections? And then it's also important for GIS data to be as accurate as possible prior to CCTV. It's also important to time CCTV closely following pre-CCTV and pipe cleaning processes to prevent the potential of changes or shifts in debris, primarily from severe storms, which frequently happen in this area. And then during the final evaluation of the project methods and results, there are a few additional items to consider when taking this approach from a small scale, such as a single asset, to a larger scale like that of an entire pipe network. And one consideration is to evaluate the full scope of the program goals and analyze the time and staff it would take to complete each stage of that process and prioritize repairs for an entire pipe network. So if we took the city of Fort Worth's pipe network as an example, if 50 miles of pipe was inspected and CCTV'd each year, it would take roughly 18 years to complete a full citywide cycle. So to conclude, this project ties to some of my current work. This is something I'll continue to work on in varying phases, with the next phase depending on the arrival of a CCTV truck. So once the equipment arrives, we will go through a training process and then a pilot phase for an in-house CCTV program. So here's a list of my references for this presentation and major resources. If you have any questions related to my project or references, feel free to reach out with my contact info on the next slide. So this concludes my presentation. Thanks everyone for your time.
All right, thank you, Katie. Looks like you've got something in the chat from Dan.
So the question is, let's see, actually, am I still sharing? There we go. So the question is, since you started your capstone project, what's changed in the city's use of CCTV for pipe asset management, increasing or improving? So from the beginning of our pilot phase, we have increased, we have both increased and improved on the amount. So I think we just did some early rough estimates on what we would be able to accomplish. And even after going through now shifting over to the digital process, we're exceeding our goals by quite a bit. So just even that, our initial estimates and scale was, we aimed a bit too low. So hopefully that answers your question. So the next question says, what kind of training is involved with field crews who use the CCTV tool? So we have not gotten to the portion of doing the CCTV piece. But all the pre-CCTV work, it took several iterations in the field. So they went through several cycles in the field, and then we kind of shifted over and adapted that into the digital. And it was actually pretty simple. I do actually do most of the training. So it's just bringing everyone in. It takes a couple days, and then you expect the next week to kind of, sit down with them several hours as people kind of trickle in throughout the day with questions. But it's really just kind of process training. We do, for our field teams, we do set up process diagrams and then step-by-step guides. Click this, enter this here. We go through very detailed process diagrams and documentation on how the pre-CCTV is conducted and how that data gets entered into the system. And it looks like there are just some additional comments, so thank you.
I saw you go through an estimate of the costs associated with a reactive approach versus a proactive approach. And I found myself wondering what it would cost to get the CCTV equipment. Do you have that information offhand, and do you have all the equipment that you would want to have to implement that approach?
I don't know the cost offhand because it does require a truck and some additional software and of course camera equipment. And then a lot of times that's typically training is involved that outside of the city, like a vendor will come in and do training with the CCTV truck. So on actual cost, I don't know on that.
Okay. That would certainly have to be factored in by any municipality that would want to follow, the approach that you're suggesting here. Okay. Any other questions for Katie? Okay, well, nice job on this, Katie. I wish you guys luck in implementing that system. And thanks to everybody, all the presenters today. Congratulations. Thank you for presenting to us. Thanks all the attendees for giving them an audience. And we will be doing this again on Thursday, same time, with another batch of folks who are wrapping up their capstones. And so we will see you all then.